In this episode,
I've never thought I'd hear the day that Brendon would say I was right.
I didn't realise it was all that kind of, which tribe are we in, and oh golly.
Buffer is like a hiding design and installation poor practice.
You're not moving the heat, you're going to have a cold house.
Volumiser can look very much like a buffer.
I'm probably giving away trade secrets here.
We are designing for less than 1% of the year.
And does it come with earplugs for the customer?
Dealing with other people's money. We can't guess. We have to do it properly.
hi and welcome to another episode of Homeowners Q&A. I'm your host Mars, and today we're delving into the contentious world of buffer tanks, volumizers, and hydraulic separation. Joining me are Leah Robson from Your Energy Your Way, Mario Dodic, heat pump consultant, trainer, and engineer, Brendon Ace from British Gas Net Zero, and Neil Soares from Grant. Welcome, everybody. But before we get started, we'd like to thank Greencore for sponsoring today's episode. Greencore is revolutionizing the way that we think about food waste with their innovative home composter. By turning your food scraps into real organic compost using tested microbes, Greencore offers a sustainable solution to waste disposal. Not only does this help reduce harmful methane emissions from landfills, but it also creates natural compost that can benefit your garden and the environment. With the ability to process up to 1 kilogram of food scraps per day and a power consumption of just 1.25 kilowatt hours, Greencore is the perfect companion for eco-conscious homeowners looking to reduce their carbon footprint. To find out more about Greencore, please visit their website, link in the description. Before we start, I actually wanted to address some feedback that we received after our first podcast recording when we actually spoke about buffer tanks. We received a lot of feedback from viewers that basically accused us of being biased by not inviting pro buffer tank installers onto the show. That is not the case. I invited, for that particular episode, if memory serves me correctly, I invited 12 what I would term pro buffer installers. They all declined to come on the show. When I decided to do this episode, I started actually recruiting about 3 weeks ago. I must have contacted about 50 installers that I have seen their profiles. So I trawled LinkedIn. I went through their websites. If I saw a portfolio picture with a buffer tank in it, I approached and said, would you come on the show? I either didn't receive a reply at all, or they just declined. So make of that as you will. But I am trying to be as objective as possible when it actually comes to creating these episodes.
I didn't realise it was all that kind of, which tribe are we in, and oh golly.
It's weird. I don't get it.
Mars, I started to be again pro buffer just because of this episode and to be a part on that side. But I think it will be a good discussion. So no problem.
Oh, you're there to prod Brendon.
Yeah. Actually, Brendon is one of the guys who switched me from buffer to anti-buffer a few years ago. So this will be quite interesting.
Right, Neil, so can you get us going today? So basically, when I look at the forums over the course of the last 18 months, I have seen that there's a mounting amount of confusion when it comes to homeowners, when it comes to buffer tanks, because the term buffer tank is just used for anything. If there's a vessel that's put in to a property, it's just a buffer tank, doesn't matter what it is. Could you give us an easy explanation of what a 4-port buffer is, what a 3-port buffer is, and what a volumizer is?
How long have you got? So, well, if we just start off with the generic explanation of what a buffer is, it's basically a battery. It's a store of water that you're going to use your existing heat source to heat this volume of water. And from that volume of water, you will pump away to the various zones that you've got. So that could be domestic hot water, underfloor heating, radiator circuits. In the olden days, the reason why we used buffers was because you had multiple sources of heat input. So you might have a boiler, you might have had a solid fuel back boiler, you might have had solar thermal, you may have had other heat engines actually pumping heat into it, and you needed one place to store it because depending on the cost of the fuel at that time of the day, it might have been cheaper to heat the stove. 4-port buffers is basically one set of tappings for input, one set of tappings for output, and then you would go to a distribution manifold. A 3-port buffer would be an input from your heat engine, but you wouldn't have a common return coming back from your heating system to go into the buffer. It would go directly back to the heat source. A volumizer is not a form of hydraulic separation that a buffer would be. So it separates, it sits in between the heat source and the heating system. A volumizer is a volume of water that sits either in the flow line or in the return line that increases the volume that the heat pump or boiler or whatever your heat engine is can use. Other people may have different interpretations, but that's how I would use the 3 of them.
So Leah, Neil actually mentioned the term hydraulic separation there. Could you just explain to people what the term hydraulic separation actually means?
It is essentially separating the flow of water that's going around the heat pump from the flow of water that's going around your house. So it can be used if you're concerned about the flow being sufficient for the amount of water that the heat pump needs to keep having circulating around. So then you would say, okay, well, we've got one flow of water that's just going through the heat pump and through the buffer. And then we've got another flow of water that's going from the buffer around whatever you've got underfloor heating or radiators on that side. So yeah, hydraulic water separation, two separate flows of water.
Mario, the other term that gets bantered around a lot is low loss headers. What exactly is a low loss header?
So low loss header is still hydraulic separation, but commonly used for bigger commercial buildings and in my experience with fossil fuels. So with gas boilers where you need to have different flow rates from for example from gas boiler to low loss header, and then from low loss header to your underfloor heating on radiators. In my experience with heat pumps, this is not quite good because you have a low amount of volume. You're just separating the system. If we will use separation, if it's needed, then buffer is better because you have a higher amount of volume. For example, in low loss header, you have few liters of water. In buffer tank, you could have 50 or 100 or bigger if needed. So basically, in my experience, we have a few cases where low loss header was installed and it was not working quite good because as Neil also mentioned, we need volume for heat pump. If you have a low loss header and on secondary side you cut off your system, then you don't have a huge amount of volume for defrost, for heat pump operating. So in my experience, not quite recommended with heat pumps.
Now that we've done the definitions, let's get stuck into the actual performance of buffer tanks. So I think the buffer tank that we most often see installed on domestic properties is the 4-port buffer. Could you just explain to us why this actually does have a negative impact on the performance of a lot of systems?
With a buffer tank or any form of system separation, the reason people put it in is if you've got different flow rates on both sides. When you got different flow rates, you get what's called distortion. When you get distortion, it brings the flow temperature down. With a heat pump or with a heating system, the temperature is the valuable commodity. Heat is just a difference between two temperatures. We need a certain temperature to achieve the output of our radiators or underfloor heating at that particular point. Now, if we have any form of system separation and different flow rates on both sides, we are reducing that temperature. Therefore, the heat pump has to be run at a higher temperature than is actually required by the system. That higher temperature results in a much higher running cost and wastage within the system. That's the reason I don't like buffer tanks or any form of system separation. I like to keep things simple. We're moving heat with water. If you're not moving the water, you're not moving the heat. If you're not moving the heat, you're going to have a cold house. The other thing people forget is that if you slow the flow rate down, you're going to increase your delta T between your flow and return temperatures. What that does to a radiator is it reduces the output of a radiator. If you increase the delta T, you've got smaller radiators. That means you have to have a higher flow temperature again to achieve the required output of that radiator. So it's a double whammy there. You're reducing the flow temperature on the heat pump and you're reducing the output of the radiators. If you reduce the delta T from 5 to 10, you've got to run your heat pump at probably 6 to 7 degrees higher than you would require if you didn't have that separation. That 6 to 7 is a guess. It could be higher, it could be lower, but it's somewhere on there. That is why I don't like buffer tanks. I'm renowned in the industry for being very, very against them. You can't be against an inanimate object. It's how it works. And it's very, very difficult to make a buffer tank work correctly. And that's why I'm against it. I like simplicity.
I just want to add that the main thing, what Brendon wants to achieve, and what everyone wants to achieve, that we need to move water from point A to point B. And if we can move this water 100%, it's never 100%, but if we could move it to point B, which is our house or comfort in our room, then we are done with everything. And with simplicity, we could achieve this. Another point, what we need to mention is that now we have heat pumps and boilers and all technology, it's modulating. What it means? So heat pump can modulate from, for example, if you have 10 kilowatt heat pump, depending on conditions, from 2 or 3 kilowatt up to 10. In that way, we don't need to store all amount of these kilowatts. That's why we don't need separation. Previously, and in commercial today, you have on-off systems, which is 0 or 10. In that case, we could use it in a form of storing the water. And also what I can agree with Brendon, but I think that design is important, because I have systems with buffer which are working much better than without buffer. This is because of the design. If you give buffer to Brendon or someone who knows what to do, the system will work fine. This is the main thing. And usually buffer is like a hiding design and installation poor practice. You put buffer and you think, okay, flow rates are fine. Also from manufacturer point of view, why people say, why manufacturer is advising on buffer tank? Because manufacturer wants to protect his unit. But I have also few cases when you have ideal installation, like pipework is good, buffer is here, but you have high running cost because we need to balance it well, and everyone thinks, okay, we will put buffer and we are done. This is not the case. Also in opposite, if you put open like direct system, but you have a lot of zoning, poor pipe works and so on, the system will not work.
So Neil, Mario said that manufacturers tend to recommend that buffers get fitted with their systems to protect the system. I know Grant don't do that, which I was not going to point that question at you at all. But there are certain manufacturers that certainly do try and stipulate or certainly recommend they put a lot of pressure on installers to actually fit the buffers. Do you think that that is a sensible approach at all?
No, not at all. It's lazy. It means that no one has actually sat down and tried to design it out. They've just taken maybe what they've done for the last 20 years and tried to shoehorn a heat pump into that installation. I can't speak for the manufacturers that are pro buffer, but I'm sure having something to sell is always very useful for companies. That's how they make the money, and that's not a bad thing. However, if the consumer is having to pay another £1,000, £1,500 for a piece of equipment that is actually going to cost them more to run it, because bear in mind, if you've got a 100 or a 200 litre buffer, you've got to heat that water before it's useful to the system. And you've always got to heat that water. So you're just adding on whatever the cost is to raise that temperature to whatever your design temperature is required all the time. I would much rather see people sit down and say, well, if we went direct, even with a proportion of zoning, even if they feel that the building regs still stipulate that you need thermostatic radiator valves in bedrooms, and you set them as limiters instead of actual room controls, it's a much cheaper install. It's much cheaper to run. The efficiencies are much higher. And I think, yes, we've got this transition where we're trying to take experienced heating engineers for the last 20, 30 years, but bring them into the low temperature game, which is completely different. You're increasing your flow rate by sometimes a magnitude of 4 to get a 5-degree differential. But running your pipe work in the way that you've always run it, which is based on a 20-degree differential, there's just so many bits of training that needs to be done there. I think we're getting there, but I think the people that decide not to use a buffer and not to use a volumizer, they're in the minority. Their voices need to be heard to actually make the transition occur faster. There is one aspect to a buffer that we haven't talked about, and that's short cycling, where an increase in volume of that proportion will reduce the number of stop-starts. So it is good for the compressor because it allows the compressor to run at a low frequency for a long period of time. And that's when we see the high COPs. But that's about the only advantage that I can see to it. Yes, it'll assist with defrost, but so would a volumizer, which is a much smaller volume.
All manufacturers will give a minimum flow rate and a minimum system, open zone system volume that's fully flowing all the time. That has to be adhered to. It not always can be achieved, and that's when a volumizer would be used. Neil's quite right to say that larger volume will can give better performance, less cycling. That can be achieved with the correct flow rates, just with a volumizer, and it makes the system a lot simpler, a lot easier. But it is a different design strategy to what the normal central heating system does is achieved. When it comes to zoning, again, it shouldn't be a problem as long as you've got your open zone system volume and flow rate, and as long as the radiators or the heat distribution system is designed correctly to accommodate the possible lower temperature in the adjoining room. What most people forget is that adjoining rooms, there's very little insulation. So that's worse than an standard external wall. And if you're only heating one room in your house, that means that room has got 4 external walls to it. And that must be taken into consideration with the design. If it's not, it will not work. That design is incorrect.
I just thought to explain to customers, a volumizer can look very much like a buffer if you don't know what you're looking at. So you might be thinking, oh no, I've got a buffer on my system. Actually, it's the same vessel. It's just piped up a different way very often. So just make people aware that you could be looking at a volumizer, you could be looking at a buffer, and you wouldn't necessarily know. The other thing I just want to say is sometimes when we're doing refurbishment jobs, and we do a lot of really big houses with quite complicated pipework and pipework that you genuinely have no idea what's going on underneath the floor and in the walls and all sorts. Sometimes it is just safer to put a buffer in. You do have to accept that there is some loss in performance, but given the number of unknowables out there in the houses that sometimes you're operating in, sometimes it is better just to put in a buffer.
Planning to install an air source heat pump? Then get your copy of Bodge Buster. It's packed with must-ask questions, real homeowner insights, and a practical guide for a smoother installation. Available in print and on Kindle. Link in the description. Brendon, you mentioned a little bit earlier, you used the word distortions. Now, let me see if I actually understand this correctly. So distortion for me just simply means blending. I don't know if that's correct or not. But in a 4-port buffer, you technically should have hot water, the flow coming into the buffer, leaving, and the return coming through the bottom and going. So if that is out of balance, I'm guessing that water just mixes, it blends inside the actual vessel itself. And that's what's causing the performance loss.
That's correct. When you blend the water, you bring down the available temperature, or the temperature that's available to the useful side or the delivery side. That temperature has to be made up by an increase in the temperature from the plant or the heat pump or boiler. When it comes to boilers, increasing the temperature does not impact on your running cost very much. Generally speaking, if you maintain your correct flow rates from a condensing to a non-condensing boiler, is about 10% performance. And that can be from 50 degrees up to 80 degree flow temperature. You might lose 10% in performance. That 10% in performance can be lost by raising the flow temperature on a heat pump by 5 or 6 degrees. It is really critical that we keep our flow temperatures down on a heat pump. The impact is significantly larger when you increase your flow temperatures on a heat pump. And that's one of the main differences between designing with a heat pump and designing with a gas boiler, is you've got to keep your flow temperatures down to maintain efficiency.
I know you can't really talk about other manufacturers, Neil, but how many of your units actually come with modulating pumps on the heat pump side?
All of them. They're all PWM pumps.
And has that been around for a while?
Since 2019. I don't think we're alone in that. We try and achieve a target, and this is something, and I'm probably giving away trade secrets here. Something that would be beneficial would be a heat pump that you could change and amend the delta T. So if it was a brand new installation in a brand new house and you can design it from the ground floor up, you can minimize the amount of equipment you put in. You can minimize the amount of control that you put in. And let the heat pump, I mean, they're so clever. You can just let the heat pump do its own thing to run at a low flow temperature and deliver those good performances. For the retrofit market, slightly different. You know, I know we've spoken before about hybrids, but if you could have a heat pump that could maybe extend that delta T range from 5 to, let's say, 10, then you can half your flow rate. And you can actually get more power through an existing radiator that's typically in the UK on a 22 mil primary with a 10 mil drop feed to a radiator. I think there's still more that can be done on the heat pump technology side that would be beneficial for existing UK heating systems without having to rip the floor up and replace the primary pipework.
So, Mario, this is something I think you spend a lot of time analyzing. Are there any measurable differences in SCOP between systems with and without buffers?
I looked at heat pump monitor, and I actually find out that there is a lot of the system in top 20 are open loop without buffer. I found one system with buffer, and this is it. I think in last 1 year, SCOP is 4 only on heating side, so we need to compare only heating, not domestic hot water. I think this is the case what I mentioned. So if you know what you are doing, you could set up things correct. Also, I analyzed few of the posts of your colleagues and find out that this is also important thing what you mentioned. So for customers, modulating pump or fixed speed pump, this is really important because modulating pump is like heat pump, which could modulate the flow rates like the outputs, and fixed pump is when you set up the speed number, it's that, and usually you have 1, 2, and 3. And usually installer put 3. So in that case, you have really high flow rate. I had one case when I was not on site. I almost replaced the heat pump itself because it was spending so much electricity just because flow rate was on 3. And there were 2 pumps with 3. We just reduced it from 3 to 1, put a little play with compensation curve, and I think we reduced around 30% only with one number. So this is what we need to understand, that this design thing is really important. And for example, if you have modulating pump and you have this distortion, you have, I don't know, 1, 2, 3 degree distortion, it is 5, 6, 7, let's say if it's 10%. But if you put number 3 and you have really high flow rate on the secondary side, this distortion is, I don't know, maybe 7, 8, 10 degrees. And we are already talking about 20 or 30% in performance. So this is what it's important from design point of view, that if we have modulating device, we need modulating pump. This is really what is also important for homeowners to know.
So, Brendon, when it comes to the 4-port buffer, the general diagram should be flow in, flow out at the top, return in, return out at the bottom. Before this episode, I actually sent you a photo of a homeowner that has just recently, in fact, then just shared that photo this week, which basically does not show that diagram at all, and it's actually showing on screen now. Is there different ways of piping buffers, or should it always be the way I described at the outset? And this homeowner that I've just showed you, they've actually got a delta T of 1, because I'm assuming that there's a lot of blending going on in there. So could you just explain that to us?
If a buffer is balanced, the water should travel straight through at the top and straight through at the bottom. There should be no mixing of the water. As soon as you start getting different flow rates on either side, you'll get the water mixing within the buffer because you don't have exactly the same flow rate running in the top and the bottom. If you get exactly the same flow rate running in the top and the bottom, you will get no distortion and there will be no loss of performance with that buffer. The picture you showed me, the heat pump came in at the top and the return for the central heating also came into the top. So now what we've got is we've got a cross flow, so the return to the heat pump is at the bottom, so the return had to come in at the top and go out at the bottom. And the flow came in at the top and went out at the bottom. So right in the mix in the middle, it all mixes together, and I'm surprised he even got a delta T of 1. That was quite a good achievement. It's got to come straight through. But that is very, very difficult to achieve. It can be done, and the top installers do it. As Mario said, some of the Some of the heat pumps with the highest performance on open energy monitor have got buffer tanks. But those guys are exceptional installers, and they really know what they're doing. They are the cream of the crop in this country. We're not talking about that. We need the mass install. We need the majority, the 99%, not the 1%. The 1% will always look after themselves and they'll do whatever they want. And they'll do it exceptionally well. In my previous life, in my previous company, I personally installed nearly 1,000 heat pumps, majority on solid stone, single glazed buildings. Never once have I put a buffer tank in, and a lot of those were on 8mm microbore. Never once was a buffer tank installed, and every single one of them performs exceptionally well. As I said earlier, if we're not moving the water, we're not moving the heat, and that's really as simple as it gets.
So, Leah, I think a lot of homeowners, when they commit to doing a heat pump, they'll probably get 2 or 3 installers come in and give quotes for a system. What advice would you give to homeowners on how to navigate conflicting advice? So if they've got one installer that comes in and says, definitely buffer tank, and another one that comes and says, well, I don't think you need a buffer tank at all, and one comes in and says volumizer, how does a homeowner balance that up?
Yeah, that's really difficult, isn't it? I would always say speak to other customers where that installer has installed, and customers who've had their heat pump in, maybe a year or more, and ask them how their electricity bills are, because that's where it's going to show. If you've got an installer that's kind of willy-nilly throwing in buffers when they're not needed, unfortunately their customers are going to have slightly higher bills. So in an ideal world, we'd all be monitoring all our systems with proper heat meters and really being able to see what's going on. But that's sadly not the case. So I think really what you can go on is customers and their experience with that installer.
Our buffer tank is 100 liters, and I see that there's a lot of installers that are actually putting in smaller units at 40 liters. Does the amount of blending differ, or the amount of distortion differ in the size of a buffer? So, is it as simple as a smaller vessel will have more blending because it's smaller?
If there's different flow rates on either side, then yes, the smaller the vessel, the more the blending would take place, or the faster the blending would take place. Brendon was talking about fitting 1,000 heat pumps, majority of which in stone floor, single glazed properties, with some with 8mm microbore. And again, it's the majority of the market that we're looking at. It's not the 1% expert. But to work out what your index circuit is, and 2, to calculate how much power you can actually get down that pipe to satisfy the demand from the radiator. It's not difficult, but I would, in my experience, say that 95% of installers and designers out there wouldn't know how to calculate that. And if that is our starting point, before we start even looking at buffers and the requirement for volume, if you don't know what the weakest part of your system is, how are you going to design the rest of the system round about it? And who's going to train that?
Absolutely right.
I've never thought I'd hear the day that Brendon would say I was right. Can you just send me this snapshot on video? I'm just going to play it on repeat forever.
Why aren't the installers being educated to actually figure that out?
Well, I think Leah hit it, in one of the first comments that she made, is that you're going into a property and you don't know what's in there. The carpets are down, the floorboards are down, the ceilings are up. You've got to use experience and good judgment to determine what this index circuit is. Once you know what it is and you can measure it and you can look at the number of bends that's leading down, you see the final tails going to the radiator, how long are they, what size of radiator when it was designed for an 8170 flow and return system. The maths isn't that complicated, but I don't believe it's being taught.
Going back to volumizers versus buffer tanks, so we touched on defrost cycles and we touched on cycling. So why aren't more installers just fitting the volumizer over a buffer? So I understand that they've kind of been defaulting to, we're going to put a buffer tank in because that's what we know. When a volumizer does exactly the same job or a better job, why aren't they defaulting to that as opposed to buffer tanks?
One of the reason is what you said, that education, because they are more safe to install buffer tank and say, okay, we'll put here as you have at your house. For pumps, everything will work, but we don't know how much we are spending. Another thing is what everyone can agree, index circuit. But I was looking at some, let's say, data or what we have. I think personally up to 8-9 kilowatt system, you could almost put in more than 90% whatever heat pump, because this kilowatt could pass, we could pass this energy or heat from point A to point B. And I think, as you said, we need to put maybe simplicity. For example, as Brendon said, okay, let's go direct. Let's put TRV or thermostat only in bedrooms. We have huge amount of water in open loop, and we need to say 4 or 5 kilowatt you could pass on 22 millimeter, 8 millimeter you could pass, I don't know, 700 watts. If we put terms like that, then we can touch this 99% what we can agree, not top 1%. What is also my experience with people are, oh, should we put buffer or volumizer or whatever? I said, you could always buy buffer, pump, valve. We have space, usually depending on the house, but I always want to be flexible. We have space, but once you spend few thousand, you don't want to remove it. So if you don't believe, let's put like this. If something will not work, we could always put additional pump or whatever. Maybe this is the best approach, and this also can give you credibility, because you are putting your money where your mouth is. Okay, we will take care of that, and you could always buy this.
Yeah, just on a slightly separate thing, I'm maybe sticking my neck out here because I'm not an engineer. I run a business. I have good engineers that work for me. But what about a situation where you're going into a property that's got underfloor heating downstairs, and it's just not possible to run the radiators at the temperature that you've got the underfloor heating is, because you know the customer doesn't want to, or you haven't got the space to upgrade the radiators to get that flow temperature as low as you're running the underfloor heating. Is that a situation where you'd need a buffer?
Can I just ask a question, Leah? What typically what would be the return temperature coming back from your radiators on?
So say you need to design the radiators at 50 and coming back at 45, but your underfloor heating is running at 45 and coming back, or 40 and coming back at 35, or that kind of difference. We do a lot of properties where people are extending, they're putting in underfloor heating downstairs, but they don't want to or can't upgrade all the radiators in the whole of the rest of the house to bring the flow temperature down.
Because of the radiators, until the customer upgrades the radiators and can start to drop the flow rate, which they should be aware of, if they don't make the capital change to change the radiators to lower the flow temperature, then they will have higher running costs. You've got to run the heat pump higher. But we could actually do a temporary design that would allow the return temperature from the radiator circuit to become the flow of the underfloor heating, and use a mixing valve. So you're not trying to split all the heat from the heat pump. You're actually taking it from a return line that's already at near enough the right temperature, and you're not mixing down hotter water just to achieve the same purpose. We've seen small increases in efficiency by doing that.
Do you need help understanding your heat pump? Then pick up a copy of From Zero to Heat Pump Hero, an essential guide offering practical advice and basic instructions for new heat pump owners to maximize system efficiency. Available in print and on Kindle, link in the description. Brendon, could you just define an open loop design for us? So is an open loop just one that doesn't have that separation in between, whether it's a buffer tank or a vessel? And is that just basically the sheer volume of water for that heating system is what's in the pipes and the radiators? Is that what an open loop system is?
To some degree, yes. But open loop, you are what you're trying to achieve is you're heating the house or the property, not the room. Your whole property will be kept, or all common areas of the property will be kept at the same temperature. To achieve that, you will have either a weather or a load compensation strategy. If you've got a higher thermal mass, underfloor heating, thick screed, you would probably run a weather compensation only strategy, because the underfloor heating buffers the heating system. Your thermal mass, you use it as thermal storage. But the open loop system allows the house to be part of the heating system, because you're not actually heating the air, which a conventional high temperature system does, or a zoned system does. You're actually heating the entire building. So the whole building is at one temperature and it stays there. If the temperature outside drops significantly, the building then supplies the buffer to maintain an internal while the heat pump catches up. What we'll generally do is only control the bedrooms, because in those areas you might want a lower temperature than the rest of the house, but you might not. If you've got something like an annex where an elderly person lives, that generally will need to be a higher temperature. It doesn't mean it has to be on its own zone. What it can be is you just design it to that higher temperature. So it's still on the same zone, it's still one zone, it's still open zone, but you might have some control just to pull that area down a bit. It all comes down to the design. The open zone system is just that, it's open. The whole system, or as much of the system as possible, is open, allows the heat pump to control directly the temperature within the property. That is where you're going to get your best performance. Generally, in an open zone system, it doesn't matter if your one radiator is getting slightly less water than it should and the other one gets slightly more. They compensate each other because they are all within one system. The heat pump has to be able to supply that heat to the property. We don't commission properly in this country. We don't commission on flow rate. Generally, that's where I've got a big problem. On the secondary side of a buffer tank, there is no flow meter. How do we know if we're getting enough flow into the property? We don't. We have no idea. That's the problem with a buffer. If you've got a proper flow meter on the other side, on both sides of the buffer so that you can balance it, different story altogether. But in general, there's no flow meter on the secondary side of the buffer tank. You have no idea what the flow rate actually is. It could be a quarter of what you require. You don't know. And that's where the problem comes in. If you're direct open zone, you know all good heat pumps on the market today have got a flow meter in them. You just read what it says, and it'll tell you how, if it's got enough flow or not. The manufacturer will tell you, I need this amount of flow for that heat pump, and it'll be a 10 kilowatt heat pump will run about 28 to 30 liters a minute. And if you're not achieving that, you got a problem. Sort it out. Fix it. You need to make sure that you've got that flow rate. And if you've got no way of testing it, how do you know? We're dealing with other people's money. We can't guess. We have to do it properly.
Mario, we've got a question from one of our viewers, and basically it's quite a long question, so I'll try and condense it as best I can. Even though we can see the reason to remove buffer tanks, they also believe that there's a reason to keep them. And they found that they help greatly in reducing defrost times and also stopping house emitters from cooling down as they get fed cold water. It also helps in stopping pipes from freezing if the heat pump is not producing heat. Without the buffer and just using an open loop, all the cold water from both the activities would flow around the emitters and cool the house down. Is that a fair statement?
Partly yes, partially not. Partially not. I have cases where you have a case like this, where you have open loop, but it's not quite open loop because you have thermostats, you have radiators, and of course, if you are turning out that zones, you will have cold water, and you could have that kind of a problem. But if you have, for example, ideal is 15 to 20 liters per kilowatt. So let's say 10 kilowatt unit, 200 liters of water. After defrost cycle, I did few analysis about that. So in 10 minutes, you have again this temperature. You cannot have such a cold water. Of course, it depends. We are now speaking generally. So each case is specific. If this customer is happy, if running costs are low, maybe it's more money to repipe this. But if it's not the case, he could speak with installer and see what is going on.
So Neil, going back to volumizers, I've seen, and I might be wrong, that you can actually install one on the flow or the return side. What is the thought process for the installer as to where they get positioned, and how does that actually impact that system?
I think different manufacturers, even installers, will have different takes on this. I'll give you my take, which might or might not be Grant's take. I haven't asked them yet. If you put it on the flow, and sorry, I should caveat that by saying that some volumizers have supplementary electric heaters in them. So you could use the supplementary heater to boost if you were outside design conditions. If it was a 3 kilowatt, you could add 3 kilowatts to the flow temperature, provided it was outside design conditions. If you've designed the system properly, then you wouldn't need that down to your design -3, -4 degrees. On the return, acts a bit faster for the defrost program, and you can actually have heat pumps energizing the supplementary heater during the defrost. So you've not just got the temperature and the volume of water that's in the volumizer, you've also could have the additional supplementary heater kicking in only during the defrost function. So it allows the defrost to happen marginally faster, but you're not impacting on the fabric or the heat within the air heat within the building. I've got a question which I would really like other people's opinions on, and it's to do with buffers, and will buffers become popular in the future? When we move to smart switching, and the energy providers start giving better tariffs for heat pumps, not just during the day, but during the night. If you do not have a heat demand at that point in time, is it worthwhile having a zoned buffer that you could either pump this heat into or take advantage of this cheaper electrical tariffs at some point during the day and hold that as a battery that you can use till it's depleted? Could there be a benefit there?
Problem comes if you're using water. Water does not hold that much heat. If you take a 5 kilowatt load on economy 7, you need over 1,000 litres of water to cover that load. Now, we just don't have that in our houses. Interesting point you say is to put it on a separate loop. That might work if you're using something like a low temperature sun amp or some sort of phase change. That might work in the future because you actually triple the volume, the energy storage in a small footprint. So that might come into play. The complexity involved and the cost involved will probably negate the exercise. If you reduce the capacity of the heat pump, it will be more beneficial than switching it off, because the heat pump will still produce some heat, but instead of producing 10 kilowatt, it's only going to produce 6. That is where I think the load shifting will benefit.
I just want to add that with this phase change materials, because water is huge and you need huge amount of the water, but I think probably not so soon, but in the future when all distribution system will be like a one part, could make sense, because at that point, for example, if you have high amount of electricity from your wind or solar and you cannot put it somewhere, you could put higher flow temperature. It doesn't matter at that point the COP is lower because you have cheap electricity, you have a lot of electricity. In that case, heat pump will become part of the system. We are now talking about, we are turning it on and off or zoning. If heating will become heating as a service, like you have with Tesla, with Netflix, in that part could be really good solution. And you have already now few of the startups who are trying to do things that way. I think this will be fine, because you don't want homeowner like you have now also on your renewable heating hub. You don't want thousands of homeowners to deal with their heating systems. And my wife usually told me, if it's not by you, I don't know how is this working. But the main thing is you have heating system, forget about this, water will move from point A to point B. And we only can do that with interconnection with distribution system, with electricity provider. This is complex thing, but I think sooner or later will come.
The only thing we haven't covered is maybe the issue of when the house is too big and you'd have to have kind of an industrial sized pump if you were going to run the whole thing open loop off one pump. I'm interested to hear what people would do with that rather than putting an additional pump in series with no buffer.
It very much depends on what the pump is inside the unit. Some manufacturers, and Mary will know, have got equivalent of an industrial pump in them already, and it comes, there's a 5 kilowatt heat pump on the market that'll give you 14 meters head at duty point.
Yeah, probably 14. Yeah.
There is no heating system in the country that heat pump cannot do. You could get a 3 millimeter microbore and it'll work.
Is that available head?
Available head. It's the same pump in the 5 kilowatt as the 30 kilowatt. My son's just put a 25 kilowatt version of that in, and he's just achieved 45 litres a minute through a retrofit system. We didn't alter any pipe work, 28 millimeter pipes, primaries, and we're achieving 45 litres a minute out of the heat pump with that pump inside the unit.
And does it come with earplugs for the customer?
No noise.
No noise through an 8mm pipe.
In my training centre, I pushed 7 meters per second through an 8mm pipe. There's no noise, none whatsoever. It's the valves, it's closing down valves that make the noise. It's not the pipe work. It's a complete fallacy. Just close a valve in a pipe, and there's your noise. As you close even a ball valve, a gate valve, doesn't matter. Close that down in a pipe and you'll start hearing the noise. It's turbulence that creates the noise. We started on a 10mm plastic microbore at 9 meters a second. We started hearing the turbulence, but the pipe was doing this as well. Try it. It does. There is no noise in pipes. We're pushing, I think it was 78 or 80 litres a minute through a 28 mil pipe with no noise whatsoever. Now, 80 litres a minute will give you 40 kilowatts through a 28 mil pipe.
This is also what is important to remember, that we are designing for less than 1% of the year, and we have really low velocity on most of the year. So even if we say, okay, for this 1% of the year, we could widen the delta T if we have this possibility with pump, and then we are done. 99%, okay, this year was, let's say, colder than previous years, but still, no problem at all.
Have you got questions about heat pumps and renewables? Then head over to the forums at Renewable Heating Hub for practical advice from thousands of fellow homeowners and heat pump users. So that's a wrap for this episode of Homeowners Q&A, and a huge thank you to my brilliant panel of experts, Leah, Mario, Brendon, and Neil. Your insights have been invaluable in demystifying the world of buffer tanks and volumizers. I'd also like to thank our sponsor, Reencool, for sponsoring this episode. Their commitment to sustainability and innovation makes episodes like this possible. To find out more about Reencool, please visit their website, linked in the description. Thank you all for watching, and don't forget to like this video, subscribe to our channel, and hit the notification bell so you never miss an episode. As always, stay warm, stay green, stay tuned. Goodbye.